remember the Stephen Hawking connection?
Yes.
Is it on the? Okay, good.
I have
because I think
very short.
here, in people, they know Stephen.
They do.
I didn't realize that.
They're very knowledgeable. You'll be surprised.
No, I didn't. No, of course. But I meant he's getting older now, so he wasn't.
But he's very famous, just like Einstein.
I believe so.
He's very
I believe
famous.
so. I believe so.
And his talks about artificial intelligence.
But I disagree. On this one, I disagree.
I'm using him to support my case that we need to think about artificial intelligence.
Then I'm against you.
We'll fight later.
I'm your opponent. Maybe you should ask the question, Jerry. Yes, of course. Yes, of course. I'll put it up here. Actually, I'll put it on the tie. How long do you want me to be? I can be short or long. What is ideal? What is ideal? Including Q&A.
Well, I mean, we can have 15 minutes or 20 minutes.
So 40, 1 hour would be a bit too much, maybe 45, 45 minutes. 45 minutes, a maximum 45 minutes.
You have some
Slides.
slides about the applications.
Yes, yeah, and yes. But will you let me know about the makeup of the audience? Is it very technical or is it business?
To be honest, I have not seen but I think it's a mix of both. I know some people are here, they're excited about the topic, but they don't know it.
Got it.
And it's a mix of
And
both.
what's your background?
Computer science, IT, I work in IT. I'm the head of the information security
Got it,
in
okay.
IT.
And you understand computational complexity?
Yes, of course.
Got it. In which case
But
do you think
I don't think everybody here
Oh,
understands.
no, right, okay.
The big O.
I'll keep it general. Yeah, I'll keep it general. So yeah,
Massive
if we
computation.
start going into the applications, we could easily take 1 hour, very easily, because the applications are specific to the industry.
Exactly. But I think it's a good idea to introduce it.
I will do that.
It's not that easy, especially for the first time.
Yeah, and I do a lot of these. Did you see my Microsoft?
Yes.
So do you want me to be at that level?
Yeah, something like it. Let's assume that they're not that technical, but there will be some people who are technical.
I'll be respectful.
Yeah, it's a mix of both.
Yes. I'll do that.
بس ناقص شموع يعني خلاص انتم منورين شموع مع هذا يلا بسم الله الرحمن الرحيم هذا شغال بسم الله الرحمن الرحيم الحمد لله رب العالمين السلام عليكم ورحمة الله وبركاته كل عام وانتم بخير عيد مبارك إن شاء الله Quantum computing is a very fascinating topic, has attracted a lot of attention recently and also many investments as well. And it promises massive computational power way beyond traditional computing, which is continuing to reach the limits of its processing power. This massive computational power could be used to solve real-time problems, real-time world problems, and will boost and transform our lives and global economies. There are many, many applications of quantum computing in many areas, banking, financial services, security, searching huge amount of data that is not possible to do right now with the current computational power, drug analysis and design, transport and logistics, and many, many others. And so today we are very honored to host our distinguished guest, Professor Ilyas Khan. He will enlighten us on this technology, its implications and impact. Ilyas Khan is the CEO and co-founder of Cambridge Quantum Computing, the world's leading independent quantum algorithm developer, which aims to develop tools for the commercialization of quantum computers. This company was selected by Bloomberg as a business innovator in 2016, and it also has a strong focus on artificial intelligence. And I think he will talk also a little bit about one of the applications of quantum computing, which is artificial intelligence. Prior to starting this company, Ilyas was the founding partner in Accelerate Cambridge, the University of Cambridge School's highly successful accelerator program. Ilyas is also the chairman of the Stephen Hawking Foundation, and I think everybody here knows Stephen Hawking, and also a fellow of St. Edmund's College at Cambridge. He is a regular and extensive writer, commentator, and speaker on topics related to quantum computing, computational complexity, and free will in the context of quantum information. He is also a life member of the American Mathematical Society. And I heard that he has some interest in philosophy, so we'll find about that maybe after this lecture. And now, without further ado, please join me in welcoming Professor Ilyas. Please.
Do you know how to turn this on?
Let me find out. It's supposed to be on.
Hello? It's not on.
It's not on?
Don't worry, I'll speak from there. I'll speak from there. Yeah, they're not. I'll speak from this one. Shall I wipe this one? Hello? Hello? Ah, right. First of all, thank you very much indeed, and I wish to apologize for the delay in the starting of this meeting. I know that you're all very busy people. I know that you came here to listen, and so therefore please accept my apology for the late arrival. Secondly, this is my second time in Oman, and I had forgotten how beautiful this country is. So I'm really pleased to be here. I'm pleased to be at the Knowledge Oasis, and I'm a guest of His Excellency, the Minister for Foreign Affairs, and so I wish to thank everybody from that ministry for making my visit so interesting. I'd like, first of all, to get a quick sense of the nature of this audience. So who in this audience consider themselves to be a computer scientist? Okay, and keep your hand up if you consider yourself capable of coding machine language code. Okay, so that's pretty much everybody. Who here is a mathematician? Very few. That's very sad. We have to change that. And any physicists? Okay, yep, we know about you, yes. And any electrical engineers? EE, mechanical, electrical engineers, okay. And the rest of you are what, business and finance or IT? Business, finance, IT. IT? Ah, okay. Okay, got it, most of you. Anybody want to admit they are businessmen or? Okay, so I do a lot of this actually. I speak about quantum computing a lot, especially in the last 7 or 8 months. And the reason for that is that, for the same reason you're here, it looks as if quantum computing is a reality. And so I'm going to be speaking probably for about 30 minutes or so, and 40 minutes we'll keep the Q&A going, and I hope that we can address most of your questions. Can we open the presentation, please? Oh, right. It's I think it's that one. Hang on. Where are we? Yep, and then which of the IT people knows? Oh, this is this full screen view already? Yeah. Yeah, it's a screen view. Okay, great. And let's just see. Okay, great. So this is not a full screen view. We need. Who knows how to put it on a full screen view? Yeah, yeah. Okay. Underneath, yeah. We can go like this. Can you see this? Is this sufficient? Yeah. Let's carry on like this. So I'm going to give you a little bit of a background first, and then we'll take it from here. But let me set the objective. The objective is that when we finish this half an hour or 45 minutes, quantum computing should not be a mystery. There's nothing mysterious about quantum computing, especially so many of you were in the IT business. And one of the things that we have to accept is that even though the words sound scary, there's nothing scary, there's nothing mysterious about quantum computing. The terminology goes back to the early 1980s. And there's two people who thought of this concept, who gave it the name. One is a very great scientist, Richard Feynman. He was a Nobel laureate. And the other one is David Deutsch, who's still alive in Oxford. And both of them thought of this idea at pretty much the same time. And the reason that Feynman thought about this idea is that in the late 60s and early 70s, one of the big challenges with computing was heat dissipation or heat consumption. So we knew how to create transistors, gates. We knew how to push electricity, but the resulting loss of heat was the generation and loss of heat was a really big issue. How do you manage the heat problem? And Richard Feynman was doing a thought experiment. He was wondering how we can avoid this problem. And of course, as we all know, nature has no such problems. One of the best examples is just a single leaf of grass. It takes sunlight and it converts it into carbohydrates, and it does it very efficiently. It doesn't blow up. So how Richard Feynman thought to himself, how can we replicate that? What do we need to do? And in his mind, he started thinking about something called quantum computing. Today, those lectures, some of them are still available. If you're interested, Bill Gates, the foundation, bought them. They're called the Challenger lectures. Some of them were delivered at Cornell. And one of them on computation is available. Unfortunately, the book is better. There's lectures on computation. But in those books, Richard Feynman explains his journey towards thinking about quantum computing. And that idea was that you could take subatomic particles. So a subatomic particle would be an electron or a photon. And you can use these elements, these fundamental elements, as the basis for communication and computation. Now, he was thinking computation. He was not then thinking communication. This was an idea which was only in the mind. In the 1980s, this was something which was probably science fiction. And for the next 30, 35 years, the story of quantum computing has been one of something which is in the distance. And the reason it's been in the distance is the engineering challenge. Now, the engineering challenge is very simple. The engineering challenge is that you have to generate, manipulate, and then measure a subatomic particle. How do you do that? And how do you do that in scale? This has been the problem. However, in the last 10 years, and especially in the last 5 years, engineering has advanced. And those advances in engineering, which I'm going to talk about a little bit, are the reason why quantum computing has suddenly become a reality. But not only has it become a reality, but the timescales keep changing. So from 1983 to 2014 or 2015, everybody was saying, oh, 10 years away, 10 years away, 10 years away. In January 2015, in fact, I have an article on this if you look it up. It's on my LinkedIn profile, I think. In January 2015, I wrote an article, and even I said we are at least 5 years away from commercial quantum computers. For the same reason that we can detect gravitational waves, for the same reason that we have this amazing technology in the particle colliders, that same learning has led now to prototype and early stage quantum computers being built. In this presentation, I'll also tell you who has built them, where they are, what they can do today, and what they will be able to do, so that we can all have an equal access to the knowledge. This is all public domain. Oh, this is great, except it's too big. Who did this? Yeah, quantum intervention. Okay, well, anyway, let's go to the next. So basically, quantum computing is nature's way of computing. Let's go on to the other thing which I think is interesting here is that in quantum computing, the reason I think it's such a beautiful subject is it brings together science. For 150 years since Riemann, and then at the later part of the 19th century with people like Maxwell, and when we came in, especially from about 1895 to 1930, this amazing growth in human knowledge, which was unprecedented in physics and theoretical physics and quantum mechanics, and of course, special relativity and general relativity. Ever since then, unfortunately, sciences have become very specialized. So if you speak to even in mathematics, you speak to a category theorist, and he'll speak then to a topologist, and they have a different language. And then you speak to a physicist, and even within physics, you have astrophysics, and then you have other types of quantum information theorists. They speak a different language. My boss is Stephen Hawking, and Stephen's language is very rarefied, although his mind, of course, is one of the great minds that has come into existence in the last 500 years. But they're very special areas of technology. Within quantum computing, we are seeing a bringing together. So in order to make the most out of quantum computing, we need expertise, particularly in physics and maths and the computational engineering areas. And that is also one of the reasons why I think the growth in this industry, in this sector, is ahead of us. I've been meeting certain people in the Omani government and other people, and one of the ways I describe this, in fact, you are a knowledgeable audience, how many million people do we think there are in the world who understand how to write computer code? How many million of people do you think? Anybody? 200 million? Yeah, I wouldn't be surprised. Certainly more than 100 million. Yeah, if you include HTML, maybe 200 million. But there's millions, tens of millions of people. I mean, you are mostly young people. Every year, all these courses in computer science are full, not just in America, not just in Europe, not just in China. And how many people understand actually how to write mathematical algorithms which are used as the basis for some of these software, especially in AI? Millions. There are millions of people. Machine learning is a commodity. In fact, there are libraries, Python. Who has tried to create some neural networks using Python? In here, loads of people. There you go. So, and there's so many. So this is a commodity. Now, in quantum algorithms, how many people are there in the world who understand how to do this? Maybe a few thousand, if a few thousand. Why? Not because they're not smart people, but because there was never any reason. And in Cambridge, for example, the Quantum Information Department, which is part of DAMT, the Department of Applied Mathematics and Theoretical Physics, the interest in this area and the interest at places like UCL and at Oxford and at Stanford and at Berkeley and at Yale, these kinds of places, suddenly, instead of getting a few dozen, you're now getting 20, 30, 40 people, I think 100 people this year at UCL. the University College in London. So this is a growing area, and it is really, really interesting. Why do I mention this? I mention this because the next time you hear somebody say, it's not possible. It's not possible. We can't do this. This is, this is impossible. Ignore them. Absolutely ignore them. We don't know what we know what quantum computers are capable of in certain areas, but the voyage of discovery is ahead of us. Just as, in the late 80s, when we had our first phone, it didn't look like this. We had no idea how this would be part of our lives. Similarly, quantum processors are just coming in. I will tell you what I think can be done, but if somebody tells you what cannot be done, my advice to you is just be very, very cautious. Now, there are certain things that we know physically quantum computers cannot do. So I think for the next 20, 30 years, existing classical computing will remain important. We have invested as a society trillions of dollars in mainframe computers and supercomputers. These will not disappear. They still have a role to play. So there will be a duality. There will be certain things that quantum can do. And we'll explore a little bit of that. So now let's talk about why there are certain things that quantum computers can do that existing computers cannot. And there is only one reason, and that reason is that quantum computers, because they operate at the quantum level, they take advantage of certain laws of nature which are not normally encountered in everyday life. So in everyday life, as an example, if I took this and he catches it, because he knows that after I applied this force, it's going to go over there to him. And we can track the location and the momentum of that bottle very easily. Thank you. And this is a very easy thing. We take it for granted. We don't even think about this. At the quantum level, that is not the case. The laws are different. From a computational standpoint, there are two laws that are different, which allow quantum computers to break the boundary. And so there are certain things that classical computing allowed us to do, and many things that you could not do. In fact, for those of you who are in IT, most existing algorithms, it doesn't matter what they are, they're the same core process, the same Turing machine. Looks down, is it a 0, is it a 1? If it's a 0, I stand still. Actually, if it's a 0, I go over here. If it's empty, I stand still. And if it's a 1, I go like this. Right? That's the same basic. That's all the computing power is. At a quantum level, and so that's why there's a boundary between what we can do and what we cannot do. Now, one of the reasons that this is a very, I wish we could see the slide in its entirety. Maybe I put it down a bit. So one of the reasons, I said earlier, we want to take away the mystery. There's no reason for this to be mysterious, but one of the human beings is we can imagine the big very easily. So if I say to you that when I look up at the stars, I'm looking, let's say, at my galaxy, our galaxy, I can tell you that our galaxy is full of other stars like the sun. I could tell you there may be 200 or 300 billion stars, and it's okay, accept that. We can kind of understand it. If we think about the extent of the universe, if we think to ourselves that our galaxy is only one of billions of galaxies, maybe trillion, we can still understand this because we can imagine the big. But when we go infinitesimal, when we go small, we really have a problem. And that's why sometimes we have difficulties understanding quantum computing. To give you an idea of scale, remember, we're not just talking about atomic structures. We're talking submolecular. mostly we're going to be talking subatomic. And one of the ways in which I help people to understand is that if I gave you a grapefruit and I said, how many atoms are there in this grapefruit? Well, there are as many atoms in a grapefruit as there are grapefruits in the whole of the earth. If I gave you the whole earth and I said, fill it with grapefruits, in fact, there are probably more atoms in a grapefruit than there are in the grapefruits in the earth. And remember, even that is too big. We're talking about, in the case of an electron, something that is 10,000 times smaller than the nucleus. These are infinitesimal things. We just cannot understand them. It's very difficult to understand them. At this scale, at the Planck scale or at the subatomic, at Planck scales of measurement and at subatomic particles, there are rules. But I want to remind you that no matter what, a quantum computer is a physical device. It is an engineered physical device. It is not something mysterious. It's not something in space. It's an actual device. So remember this. And all devices follow rules. And the rules of quantum mechanics have been experimentally proven for almost 100 years now. There are two rules which create the magic of a quantum computer. The first rule is quantum superposition, and we're having some audience participation, I think. Does anybody want to explain superposition at a quantum level? Anybody brave enough? Oh, we have some physicists here. I forgot who said. Well, we know we have one physicist. So the gentleman here said it's a status. The gentleman on your left is actually the one who should be saying, but he's keeping quiet. Okay, so superposition is if you do nothing else after this lecture and you learn about superposition, your life will be changed. I thoroughly recommend it. So superposition is like this. So first of all, we'll talk about superposition as a principle, and then we'll apply it to the quantum computer. In quantum mechanics, a superposition means that if you have a particle, when I threw this bottle to this young man, he caught it, and we could tell where this bottle was and how fast it was going. At the quantum level, we have no idea where we can precisely measure all of the different measurements available for that particle. If we measure its momentum, we don't know its position. If we measure its position, we don't know its momentum. Moreover, in any given system, that particle, let's call it an electron, has a probability of being in every single position at the same time. Now, let me explain what that might mean. Can you imagine, remember we were talking about the grapefruit. So the grapefruit is a sphere. So let's now think of a basketball. You all know what a basketball is. Think of a basketball, but don't think of the surface of the sphere. Think of it as an object that's got a center and the coordinates of the center. Yesterday I met somebody who was doing pi calculus. He's not here today, is he? Okay, anyway, it doesn't matter. So a basketball has, at any given point, I could give you the coordinates, and you can find a place in the basketball. So if I drop something in the basketball, it could be up here, it could be on the surface, it could be at the center. There's a three-dimensional way of measuring, Cartesian measurement in 3 dimensions of where any point could be in the basketball. Imagine, therefore, a particle that could be at any place, at any time within that spherical object. That is superposition. But when you measure it, you get an answer. It gives you an actual answer. Now, in computational terms, the answer we're looking for is a 0 or a 1. Why? Because information is coded in zeros and ones, yeses and nos, in logic. And so when we measure a qubit at the point of measurement, even though previous to measurement it was everywhere, at the point of measurement it is a 0 or a 1. Now, please remember that, and you are 50% of the way to knowing how a quantum computer works. So this is 50%. The next slide is the next 50%, and we're all, well, maybe not experts, but we know how it works. We understand how it works. The second is quantum entanglement. This is another rule of quantum mechanics. This one is, well, Einstein died worrying about quantum entanglement. And to be honest with you, we don't understand why quantum entanglement works. There are many different philosophies, many different approaches, but we do know it works. What is quantum entanglement? Quantum entanglement is when two particles, an A and a B, an Alice and a Bob, or you could call them Adnan and Betty or whatever, no matter how far apart they are, they could be at the end of the universe. By looking at one particle, you understand the state or the information of the second particle immediately. One of the laws of relativity, one of the laws of the universe, is that nothing goes faster than the speed of light. However, on the surface, this appears to break that rule. Now, there are many different explanations, but there are also many tests which have proven again and again that this works. So this is the second part of the rules of quantum mechanics that we use in a quantum computer. The first is superposition. The second is quantum entanglement. There's a really good video on the IBM website. Anybody here from IBM? Yes, you're an IBM person. Right. It's a great video, right? I highly recommend it. It's an animated video, and it explains how superposition, the quality of superposition, the quality of entanglement is used. Okay, so this is the most technical part of the presentation. Now we're going to move on to building the machines, who's been building them, and how can we use them. Because of the nature of a quantum computer, due to the rules of quantum mechanics, one of the empirical results of using a processor like this is obviously an increase in power. What we mean by that is a number of steps, the number of operations that can be completed in a single measurement are much greater, in fact exponentially greater, than a classical bit. And I've just given you some data here. There's a little bit of approximation here, but the second bullet point says that a quantum computer with 500 qubits is more powerful than all the classical computers in the world connected together. So if you took every single supercomputer which exists, if you took all the iPhones, if we took all the laptops, and we somehow connected them together, they would be less powerful computationally than a single 500 qubit machine. Let's carry on. Actually, this is a very important slide, so let's come back to this if there's some Q&A. Well, I mean, what does this really mean? We can come back to. So why do we need quantum computers? What can they do? I think everybody here is familiar with the traveling salesman problem. This is a NP hard, NP complete problem. Classical computers have no chance to solve this problem. And this little slide tells you that by the time you get to 22 cities with 10 to the 19 routes, a classical computer, which is defined as the 4.4 gigahertz speed, clock speed, would take 700 years. And if you just go and increase this to 28, which is almost a quarter, the increase, of course, is exponential. So remember, at the exponent level, you double per digit, so it doesn't go from 19 to 30. 19 to 20 is a doubling, 20 to 21 is another doubling. So it basically takes you the life of the universe to solve this problem. So this is the kind of problem that people are confident and hopeful that a quantum computer might be able to become more efficient. This is an open question, and I think it would be wrong to suggest that we could do this with today's quantum computers. You cannot, and I'll explain why later. But in theory, at some stage in the very near future, these types of problems, optimization problems, for example, will become accessible. And I'll give you a timeline. I'll give you my opinion about timelines. This is a very scary slide. This is taken from Microsoft. The Microsoft website on quantum computing is just as... this is a public lecture. This slide is available. Anybody who wants it. Now, logistically, I'm going to give you my email address later. And if you want this slideshow, I'm happy to send it to you. There's nothing private about this. Everybody knows RSA 24. Well, everybody knows the RSA convention for encryption. It uses prime factors. RSA 2048 is nothing special. It's just a method of looking at a digit with 2048 bits. Existing computer would take a long time. I actually took this from the Microsoft website. They have a big project on quantum computing, and a quantum computer would look at that and probably resolve it, well, they claim in 100 seconds. What is not included in this page, of course, is the definition of what size and type of quantum computer. I think that we are a few years away from breaking 2048, but perhaps not quite as far away as we might once have thought. At some stage, the view was we would take 25 years to get to this stage. Again, I'll explain why that is the case. But these are two examples of common problems that are impossible for classical computers. Now, for the same reason that a quantum computer or any computer might be able to resolve these issues and these types of problems, there's a whole world of applications that open up. And a lot of you are from business. It's really difficult. It's impossible to find an area of industry that won't be affected. Some industries will be affected 10 years from now, some years 5, some this year, some next year. But the main thing is we have to be quantum ready. If you are in a large organization and your planning is a 3 or a 5 year plan, you have to know how quantum computers will affect your business. You have to. And if you hide and you pretend it's not happening, that's a very dangerous thing. I'm going to come back finally to this slide and bring many of the things that we've discussed together, and we'll just go industry by industry because I think you might be interested in this. So I'm going to come back to finish on this slide. Maybe we don't need to spend too much on this slide, but the point of this slide is a little bit about, so my organization is called Cambridge Quantum Computing, CQC. One of our products we have is called Ticket. And Ticket is an operating system for quantum computers. And we, a couple of years ago, we were successful in resolving a long-standing problem in circuit complexity. So we designed a compiler. One of the quantum computers that exists in the world today is the project at Oxford. It's the UK government project. And one of the modules in the compiler is being built, has been designed and will be built by Cambridge Quantum. The reason I mention this, however, is, and that's, if some of you are interested later privately over coffee, I can explain to you exactly what that is. But the reason I put this up is that ultimately users could even be people who are programmers, will still program these machines. They're no different from any other machine. High-level languages will interface with a compiler, and the compiler will then manage the different hardware. There, at the moment, is no standard on hardware, and I'll explain who this, in fact, the next slide I'll move on to now. I don't think we need to spend too much time on the compiler, unless somebody really wants to talk about it later. Okay, so who's doing what? The leaders at the moment, Google, first of all. Anybody here from Google? Anybody work for Google? So Google have a very advanced program. They have a team in LA off Venice Beach, and they also have a team in Santa Barbara. The team in Santa Barbara was from the University of California, Santa Barbara. They acquired the whole team, and they are building they have built a quantum computer based on superconducting technologies. They're generating, remember I said you first have to generate, manipulate, measure a qubit. So the method that they've used is a superconducting methodology at cryogenic temperatures. And they have a gate-based computer. What that means is that it follows, it's a universal computer. It's capable of being programmed. It's a small scale, but they have publicly, Google have publicly announced this year that during 2017 they will achieve quantum supremacy. So this is not me telling you, this is Google saying it. I strongly encourage you, if you're interested in this, to look at what Google are doing. They're a little bit more secretive than IBM in some respects. The reason for that is that they're building a machine for themselves. And that machine will be delivered to clients over the cloud. So they have a high-performance computing initiative, and you can buy computational assistance over the cloud, not just processing power as measured in traditional terms, but also applications that run on those high processing powers if you wish. And they will add quantum computing to that suite of services. I was in Munich 2 weeks ago with, we work with Google. We're one of 4 companies that are working on the algorithm side with them at the moment. And their machine might, by the end, well, not might, they've said that by the end of this year should have at least a 50 qubit size, 50, a 2 qubit gate fidelity of 99.8, and the journey from 50 to 1,000 qubits and 999 fidelity, well, who knows, but it's certainly not 10 years. Now, they don't have surface codes for error correction, so I'll come back to that. You're a technical audience, so if anybody wants to ask about that in the Q&A, we can talk about it. The other people in the lead, I'm not going to go through everybody, is IBM. IBM unveiled, they have a different approach. So they're in the public domain. They have unveiled a 16-qubit machine, and anybody here can access it from the internet in order to test a quantum algorithm. Has anybody done that? So some of you who are programmers, I hope you do. It's an amazing experience. Now, the reason they're doing that is twofold. They are building a machine. They will be selling their machine, either through the cloud or as individual appliances. But I think they're being very, very smart. By opening up to the world an interface for quantum algorithms, what are they doing? They are getting free innovation. And that's how things work. That's how they should work. So this will advance very quickly. They already have a 17-qubit machine, which is for enterprises, and I don't know how long it will take them to get to the same level, but they're in the race. Microsoft, keep your eyes on Microsoft. Some of you who are older will remember in the 70s and 80s, there was, 70s actually, video machines came and there was a fight between Betamax and VHS. Who would be the standard? So in a similar kind, there was another fight during the mobile platforms, of course. We don't have a standard, but if there is a standard, it might well be Microsoft's. Why? Microsoft have chosen to build a quantum computer using topological quantum qubits, something called the Majorana fermion. It doesn't matter what that is. But what it means is that their machine will operate at room temperature. It's not a superconducting machine. And most important of all, although at the moment they're generating, one of their projects is generating qubits using superconducting methods, they would not, a topological quantum computer would not need surface codes. It doesn't need error correction. That's a big, big plus. So you can scale very quickly. You can start doing things which are unimaginable without error correction. That's Microsoft. The Chinese, through Alibaba and the Academy of Sciences, announced earlier this year that they have a machine and that their machine will be more powerful than a laptop by the end of this year. This is all in the public domain. A few weeks ago, the Chinese also broke the record for quantum entanglement. They sent up a quantum satellite. For those of you who are interested in security, cybersecurity, hacking, obviously, if you're going to be quantum resistant, you have to have a quantum method for sending and receiving information. And the Chinese broke that record last week. I think it's 3,500 kilometers. The one at the bottom, Enquit, this is the UK machine. It's being built in Oxford, and this is machine I referred to earlier. So these are some examples of what's going on. There are one or two startups also who are building machines, and we ourselves are agnostic. We love everybody who has a machine. We're not involved in building the hardware, and we're working with pretty much all of these people. Not every name on here, sorry, all the people who are involved in machine building. Lockheed Martin was one of the early adopters of looking for applications. Fujitsu have a big program going on. Volkswagen, earlier this year, was looking at traffic management, I think in Frankfurt or Munich, using a quantum platform. The list goes on, and every day the list increases. Right, timelines. Let me just see what the next. We skip this one, and we'll come back. How are we for time? 5 minutes more, is that it? Ah, okay. So, yeah, let's go to the industry slide then. We'll go back. Sorry for this. Right, let's finish on this slide. Up until now, most of the machines have been quantum machines, the prototypes, have been prototypes where the primary interest is by governments. Why? Because governments are concerned about security, they're concerned about the platform. What I mean is by that is the infrastructure through which we send and receive messages which might be sensitive. It's become clear that quantum computers will change the rules, and governments are focused on making sure that they understand how the rules will change and when. The US government has been funding research in quantum computing through IARPA and DARPA for many, many years. And the UK government took a lead on this because they allocated specific money to build their own machine. So governments have been focused on intelligence and security. That has been their primary focus, and that remains their primary focus. There was some concern that governments will keep the machines to themselves. But this is not my concern. I do not believe this will happen. There are too many initiatives, there are too many things going on. The Chinese and the Russians, well, I shouldn't say too much about the Russians because I don't know, but the Chinese initiative is clearly driven by the state. In the 2013 five-year plan, the #1 priority for the Chinese government was quantum computing. You cannot send a satellite with quantum-enhanced technology, which they did last week, unless you planned it 5 years ago. They are spending billions. There is no limit to their budget. It is their priority. And if you listen and read to why, it's obvious why. They believe that the world of technology, there's no bigger disruptor. There will be no bigger disruption to technology than quantum computing. You can be skeptical. People can say, 10 years from now. But you know this will happen. And when it happens, you have to be there. And the Chinese recognized that years ago. And now it's coming to fruition. On the intelligence and security side, this is the least of my areas of knowledge. One of the things that my company has is the patent for true randomness for the first time in human history. We've never had randomness. We have pseudo-randomness. We have seeded randomness. So using a quantum platform, you can have certified device-independent randomness. And the intelligence industry would need that. You need randomness. Now, on financial markets, of course, there's one thing that everybody is worried about, which is machines trading. Already, the majority of trading in all the big stock markets and commodity markets is driven by quantitative methods, by machines. Some because they're fast, some because they're accurate. But this is like playing with an abacus. A quantum computer has the promise for dimensions of information that we cannot currently see, but which a quantum computer will be able to see. I think this will make an equal playing field. This is supremely important. But even though those two are nothing, who cares about making money from stock markets? It's not going to change humanity. What will change humanity is medicine and drug and energy. These are the things we should care about. The genome, drug delivery, individual drugs for the individual person. This is all quantum chemistry. This is all, well, not the genome, that's a separate issue, that's data. But can you imagine if we're able to create new materials, which currently we cannot? Quantum simulation, I think a huge percentage of all supercomputers are used for quantum chemistry or chemical or molecular simulations. And with a quantum computer, even with early stage quantum computers, we have the ability to create new materials. This is something which has not been within our grasp. Before it was trial and error. We don't know what's going on at the quantum level, at the molecular level. This is very exciting, and this will happen even with some early stage quantum computers. Our company is working on some molecular quantum chemistry algorithms looking particularly at one or two structures. And the energy industry, why? Well, of course, there's one obvious answer, which is photovoltaic. I guess in the Middle East, with our heritage of looking at oil and gas, this might be a little bit difficult to accept. But this transforms the solar energy. Suddenly, instead of having a few percentage points of efficiency, we can have smaller devices that are 80, 90% efficient in converting sunlight into energy. So these are some of the things which where there are many, many others as well, but these are some of the areas in which we have applications. So when will this happen? I'll finish now. There was a meeting last 2 Thursdays ago in Munich. All the big guys were there, Microsoft, IBM, all the big names, governments were there, all the leading universities were there, all the leading players were there, we were there. And one of the questions was, how can we explain to the world what is going on, and how can we say it with one voice? Because we don't want to confuse people. We don't want to scare people, and we also don't want to give them false information, speculative information. How can we become standardized? So there was an agreement amongst everybody that what is sensible, of course things may change quickly, but what is sensible is the following. We believe that the Google paper, which was published in February in Nature magazine, very easy to find, they said that within 5 years, quantum computers will be commercialized. That means they will play a part in all our lives, to a greater or a lesser extent. So I agree with this. In fact, I think some commercialization will happen in about 2 years' time, and I think it will be in quantum chemistry. The other area where it will be happening quicker, and you have to be careful on this, is artificial intelligence. Something called quantum machine learning will accelerate very quickly, not on the existing machines, not on 50 qubits, but once you start getting slightly bigger machines, suddenly you can enhance machine learning techniques, particularly neural networks. When will we have universal computers that can do anything? Well, this requires error correction, unless Microsoft have a machine. So I'll leave you with two thoughts on timing. Number one, I think surface codes which allow fault-tolerant universal quantum computing at scale is probably 6 years at the earliest, 8 years at the latest away. Doesn't mean we can't use machines in the interim, we just can't use them in the same way. So I always remind people that the Apollo space program used computers, and the journey from 1967 to 1979, when you had the IBM PC, was only 12 years. This will be quicker than that by half, in my opinion. Could even be quicker. But that's what I would suggest you think about. However, there's one outlier. What is the outlier? Microsoft. If Microsoft design and deliver a topological qubit with a machine that has some scale, then all bets are off. It could happen. It might happen a little bit quicker. I don't work for Microsoft, so this is not PR, but in November of last year, they made one person in charge of quantum. Does anybody know who that was? Any Microsoft people? Any shareholders of Microsoft? If you are, you should be happy. They made Todd Holmdahl in charge. Todd Holmdahl is an engineer's engineer. He's not a theoretician. He makes things. He builds things. He built the Xbox. And he is in charge of their quantum project. And he was interviewed recently, very recently. And he said, this is now an engineering challenge. I don't know how old he is. He must be 57, 56, 57, I guess. And he said, the machine will come before he retires. And every week now, there's some other new breakthrough, which there was a company in a spin-out from the University of Maryland called IonQ. They made an announcement saying that their machine will be ready next year, commercially available. So on the machine side, engineering is advancing quite quickly, because it's no longer in the universities, it's in business. Business people are building these things. So I think, yeah, we have time for questions if you wish, yeah.
Thank you very much, Professor Ilyas, for the very interesting lecture. We will now open the floor to Q&A. So please make sure that to mention your name, your organization, and stick to one question each, please, so that we give chance for others to ask. Over there, please.
Thank you very much for this enlightening us on the quantum computation. My name is Sultan Yahyai, working for electricity company, but I'm a researcher on numerical modeling, basically. My question is related to quantum readiness. During our journey from shared memory computer to a distributed memory computer, we had difficulties on changing the programming paradigms. So my question is related to the programming paradigms moving from traditional classical computers to quantum computers. And on the same aspect of quantum readiness is basically, we have challenging on understanding the science itself. So for example, when we work for 3D solar radiation, we have challenging on simulating such radiation, but on the other hand, we have challenging on understanding the science of 3D solar radiation itself. So how do you see that scientists from different science disciplines would cope with the quantum computation? Thank you very much.
I think, first of all, I'm very, very optimistic. I think that most operating systems for quantum computers will be adapted for existing high-level languages. I think the challenge is going to be obviously on the quantum algorithms. But I can't remember how many, but there's about 100 or maybe more quantum algorithms already. They're kept at the NIST, which is in Denver, Colorado. It's public domain. There's no secret on this. And I think, my oldest son is 12. By the time he's going to university when he's 18, this will be a few thousand. The science actually is well understood. Quantum mechanics is one of the most experimentally well understood sciences. And so therefore the application of gate-based programming to take advantage of superposition and entanglement is something which I think will accelerate. Now, the question of alignment between the algorithm and the platform, this is more complicated. And in this area, I think that it is my opinion that the quantum chemistry area will be an absolute trailblazer. Now, you, I think, are aware that in fertilizers, as human beings, we're hopelessly inefficient. So Haber-Grosch, I think, is the challenge. So I think that if I look forward in 3 years, just 3 years, I think the algorithms that help us unlock quantum chemistry problems could be utilized in other areas as well. Why do I say that? Because even in classical computing, it's only a handful of regimes, a handful of protocols that we then adapt. So that's my view as far as the science is concerned. I don't think there'll be a big problem creating these algorithms.
I'm from Innovation Center. I'm a bit interested on the disruptive technology perspective of philosophy. If it is still the R&D is part of the supply chain of quantum computing here, don't you think that we are a bit optimistic in the commercialization process in taking this technology to the market? Because you just...
It's a really fair question, young man. It's a fair question. So I think that it's always better for somebody like me to answer in two ways. First, to give you a couple of facts, and then to give an opinion. So I don't think there's any reason to speculate. There's no reason to speculate. Firstly, commercialization means having access to a machine. That means a company must have access to a machine, and the machine must deliver something which makes its product or service better than it was before, and which they're willing to pay for. Right? We agree on this. Now, if we agree on this, then clearly today there are 4 companies which possess quantum computers, which possess customers, and which have publicly stated that they will be commercial. These are companies which are large. They're not startups. IBM is one. As I said, Google is another. Now, in this area, they're they're not speculative. They're saying just focus on certain areas like quantum chemistry. The disruptive nature of quantum technologies, in my opinion, initially will be in security and in the Chinese initiative, which I mentioned earlier, the internet. They have stated that they want a quantum secure future. This means that all of us here, if we are worried about our security being breached, we should not waste our time trying to buy a quantum computer today, but we should create a quantum readiness program so that we ourselves quantum. This will take 4 or 5 years, but when we talk about disruption, This is the pure definition of disruption. Everything that people talk about, Uber, Airbnb, Facebook, these were not disruptive. These were enabled by the disruptor, which was the internet, right? So this is far, far, far bigger than the internet. The time scale, I would recommend that you do a little bit of your own research, but I think that cloud-based access to quantum computers will come first. So you have to be a customer of Google and a customer of IBM. I hope that answers the question.
What about the two disciplines, the augmented reality and self? Where do you see this?
This is something, your opinion on this is better than mine. But I met the Google guys, obviously. I think that their own quantum computer could enable their tracking system. The new one is called LIDAR, I think. I can't remember now. Augmented reality, because we have a big audience, please talk to me and I'll give you my opinion on what's happening. But I think augmented reality is a tiny part. It's not a big part. In the next 3 years.
Hi, Abdullah Al-Maskari from Assas. Assas, Muscat National Development and Investment Company. A few years ago, D-Wave announced the availability of the first commercially available quantum computer. However, there was a lot of speculation, a lot of back and forth about it actually being a quantum computer or not. So how come we ended up in a situation where we have a physical machine in our hands and we are not able to verify that? What was the challenge?
Oh, this is the easiest question I've had. I'll shout. This is not very good. So, first of all, D-Wave is a commercial company, and at the time of its launch, one of my scientists was one of the test pilots. In my company, we have people who have spent a few hundred hours programming D-Wave. We're very familiar with the company. At each point when D-Wave was announcing something, there was a scientific community of test. If business and investment ignored science and focused on the announcements, that's not our problem. So there's a guy called Scott Aronson. You can go onto his blog. It's a blog for 7 years, no, longer, maybe 10 years. You go back to 2010, 2011, 2012. He did some independent tests. There was always independent verification. Now, I know the D-Wave people very well. I'm very respectful of them. So their machine, I didn't mention it here, I should have done. They have a different approach. They're doing something called quantum annealing. And there is some optimism that it might have some benefit in the future. Up until now, it hasn't. I think they've got, I don't know how many customers. Lockheed is a customer, NASA is a customer. The Volkswagen thing I told you about this year was done on a D-Wave machine. But Google has a machine as well, that's right. But they share it with NASA. It's at the AIM Center. So the fact of the matter is that as of today, there has been no verifiable speed up of any generalizable problem on an annealing platform compared to a classical platform. So I think this is not something which is very difficult. Now I'm going to give you an opinion. So I've just told you facts. Now as opinion. I think that the Google machine, the superconducting machine, the IBM machine, the Microsoft machine, the Enquit machine, the IonQ machine, there's another company called Rigetti. I think these machines are advancing very fast. So I think D-Wave has a bit of a challenge. But they were pioneers, but they have a bit of a challenge. Yeah.
Assalamu alaikum. Ali Shaydani, Research Council. Moore's law states that the number of transistors double in every 18 months. Is there a Moore's law equivalent in quantum world?
Not yet.
It's an opportunity.
Kahn's law. Well, I'm not an experimentalist. Obviously, we're on the algorithm side. No, you know what? The real limit is at what point subatomic becomes macro. When does quantum stop being quantum? At what stage do the inherent qualities? May I ask, are you a physicist or?
No, I'm not.
So there's a really interesting new area where the answer to this question might come. And there are some people looking at something called ER equals EPR, which is all about black holes, and the fabric of the universe is made up of entangled bits. From the time of the Big Bang, the vast majority of this, and basically it's a computational model. Hidden, no, not hidden, but within that area of research may emerge some of the answers to these questions. But at least for the next, in my opinion, at least for the next 10 years, I think that the challenge of increasing the number of qubits and at the same time getting to 9999999 in 2-qubit gate fidelity will be the real challenge. And this idea of sentient neural networks, which everybody talks about when they start talking about millions of qubits, this is philosophy. Then I have no opinion. But we don't have one at the moment. I think if you've got 100 people who were engineers working on these programs, and quantum interference, yeah. And if you did a blind survey and you said, at what stage will we get to 1 million qubits? Now, this is an arbitrary number. I mean, do we really need 1 million? You know, with 50,000, we might never need any more. But anyway, I think that the consensus of those 100 would be more than, 10 years, they would say. But see, 10 years is just a...
It's Nasser Ismaili. First of all, thank you very much for the wonderful lecture. Also, you made a complex subject very simple to understand. My question is, at the moment, we are relying more and more on the technology, from smartphones to smart televisions, self-driven cars, IoT, cryptocurrency. And I think one of the airlines announced self-flying commercial airline. This is on the side where there's a security to protect it. On the other hand, we are having this massive power computing that might be able to break this security. So, shall we be worried about the future, or what's going on?
First of all, down? Okay, sorry. I apologize. So for 1 hour I've been doing it's a great question. Okay, first of all, before I answer your question, listen, Bitcoin and blockchain, I meet people who are evangelizing about investing in this, and I really wonder what planet they're on. You cannot invest, you cannot commit a company's future on technologies which require public key distribution. You cannot. Even if we are skeptical, I know you didn't say this, but you mentioned cryptocurrency. Even if we are skeptical, even if we say that a good quantum computer is 5 years, 6, 7 years away, the investment you make now in any technology that requires public key distribution is at high risk, not just from quantum computing, but other high-performance computing. So this is just so please don't rely on these quantum currencies unless you know something which the rest of us don't. Yeah. And, well, we have a program, as I think I mentioned. I went to a government agency before, last August, for 3 months. we were easily mining Bitcoin. We didn't do it to make money or to hack, but it's not difficult. Or it's less difficult than people make out. Of course, there's a wonderful way of being secure. If I have let's say that this is $100, and let's say I cut it, and I gave you half and me half, there's no quantum computer that can break that, right? So there are ways in which we can enhance our security. Forgive me, that wasn't your question. So your question was about should we be worried? So there are some people around who are talking about AI, artificial intelligence, is an existential threat to humanity. What they mean by that is in the next 100 years, the whole of humanity is at risk from AI. My response is that I think if you told me I'm worried about the weather on Mars tomorrow, it might be too hot or too cold, I think this is more relevant than worrying about this. Of course, over coffee and have a cigarette and chat, I think, but really, honestly, I think that we ourselves have a great deal more capacity for good than bad. You can disagree, you can call me an optimist, but I do not believe that we should be worried about those things. I think we should be embracing the things that change our lives for the better. How long has there been human existence? 10,000 years? Recorded civilization for 4,000? Some of these things we're going to resolve within our lifetime. Well, maybe not mine, I'm too old, but most of you guys. These are things we've dreamt of doing. And if we worry about the negative impact, we're worrying about the wrong thing. This is my honest opinion.
But I think what he's saying, should we be prepared for it? How do we be prepared?
This is a question I cannot answer easily. This is a big, well, okay, let's make it a small question. Let's make a small question. So one small question is quantum readiness. How can we be quantum ready? This is a good question. So I think we should all be quantum ready. And the best way, my recommendation is, especially for governments and large organizations, you have the in-house capability, you do not need to rely on others, and you can start doing your research now. As a country, never mind a company, you are not behind anybody. You're at the starting line. And I think if you developed, my opinion would be develop an expertise in quantum algorithms. This is something which is within your grasp. In 5 years' time, if you had 5,000 people who were Omani or from the Gulf who were competent in quantum algorithms, you'd be right up there. So I think these are the things that, that I would recommend.
Assalamu alaikum. I'm Sheikha from a TTO office in the university, Sultan Qaboos University. And mainly, actually, like you said, there is the quantum chemistry and quantum algorithm that need to be focused to resolve it. But that will lead me to the question of actually having property over, the result or the outcome of that research. Because that's why maybe the companies, they are not focusing much on algorithm because they don't have, the opportunity to patent it. And the patenting, that's why they are coming more into the devices and computing side more than algorithm side or chemistry, quantum chemistry. That's my interpretation, actually. I don't know your opinion because in the recent years, especially in 2014 and 15, there is an increase in patenting in the quantum computing, and from those companies, and a lot on the U.S. office also. But what is the mechanism in order to get patent in that area? It's still in the very early stage. It's a methods,
Yes, so this is a, maybe I'll give you a short answer. My company has 2 patents for quantum protocols. They're not devices, and there's no problem. So I'm sorry to hear that you have such an impression. It's factually incorrect. Now, you have to show that it can, as you know, in the US and the European patent regime, you have to show that there's some device independency. So you have to show how a device would operate that. But software is clearly something which it has been a problem in certain areas, and algorithms have been different from software. But when I use the word algorithm, I assume, and I apologize, I assume a conversion from an algorithm into an application. The application can be protected. On quantum chemistry, you know, I would, if I were you, I would rethink your opinion. The balance of power has shifted to corporates, and companies who are involved in quantum chemistry are themselves the one who are creating this change. So we are working with a very, very large global company which is involved in synthetic materials, and it has identified 2 or 3 materials, and we're doing a quantum algorithm to allow them to diminish the time and the risk in looking at new molecular structures. So, you know, the atomic spectra, basically, the calculation that goes into that. So I think that's happening. It's not happening. And actually, it's not happening in universities. It's happening in the companies.
What is the technology gap in that area?
The gap?
The gap. You know, the technology analysis, when you do it globally, in that area in quantum computing. In your opinion, what is the technology gap?
It's a lack of qualified. Well, first of all, designing quantum algorithms is very, very hard. It's not an easy task. As I said before, if there was one gap, it is in competent people who understand how to design and build applications based on new algorithms. I think that, like I said, there's a few thousand people in the world. That's the gap. And that probably, if we're sitting here in 5 years' time, there'll be 100,000 people, because there'll be demand for them. Previously, there was no demand. There was nowhere to work. There was no jobs.
The last question. Last question.
Thank you very much. Shidani from SQ. Can you kindly elaborate in the effort for quantum telescopes?
I don't know what a quantum telescope is. I'm sorry. Is it a? Sorry,
I thought using the quantum entanglement, you can know what's happening in the other side of the universe. Here.
Well, quantum entanglement is a big subject, and I apologize if I miss. So what you can tell is not what's going on the other side of the universe, but if you have a particle that is on the other side of the universe, by knowing the property of the particle here, you automatically know the information encoded in that particle, not the rest of the universe. But what I would say to you is that the research on the physics of black holes and the singularities that they represent, these do provide a link, a path to unearthing the essential mystery of the universe. But this is, I'm afraid, not my area.
Thank you very much.
Thank you very much. So I'll ask you one more question. As a moderator, I have an exception. So you talked about a few times about being quantum ready, and we understand it from the capacity building point of view, research point of view. And what about infrastructure side? How can we be ready because when it comes, for example, to quantum encryption, my understanding that quantum encryption works currently on fiber links. And so how can we be ready from an infrastructure point of view if we're going to see a commercial quantum computer within 5 to 10 years that's going to break all of the traditional encryption algorithms like the RSA and other ones? This is going to cause a collapse on the whole e-commerce and the internet.
Well, I think there are two questions there. And first of all, I think we have adequate infrastructure. As long as we've got fiber optics and, of course, satellite-driven communications, I don't think it's an infrastructure problem. I think that when quantum computing comes along, one of the biggest challenges in that is not something we can solve as customers. It is quantum memory. So scaling, something called QRAM, or there are different ideas about this. This may be a constraint in terms of doing really big things. Well, not all quantum computers will be superconductors, but those that are clearly cannot just be bought like a laptop. So I think these will be at the enterprise level, and there'll be many things which classical computers still will be doing, even in 10 years' time. So I think it'll be at the enterprise level. I also believe that the power of quantum computing will be delivered remotely. I think that's probably my view in the short term. I just want to clarify something on quantum encryption, on hacking. I think it's an unanswered question. At what stage will we break RSA 2048 using a quantum computer? The most optimistic people might say 2 to 3 years. The majority of people will say 6 to 7 years, and then maybe 10 years is the outlier. I think that's the scope. Of course, tomorrow somebody may do so. And the reason for that is you still need error correcting techniques, which we don't currently possess, unless, like I said before, unless Microsoft builds qubit. Well,
Thank you very much. Thank you very much, Professor Ilyas, for your time and interesting lecture, interactive session. Wish you a very pleasant stay in Oman. Enjoy the weather as well. شكرا جزيلا لكم على الحضور وإثراء النقاش. Have a very good day. Thank you.
Hi, Abdullah Al-Maskari from Assas. Assas, Muscat National Development and Investment Company. A few years ago, D-Wave announced the availability of the
companies.
What is the technology gap in that area?
The gap.
The gap, you know, the technology analysis when you do